Good afternoon, everybody. I'm actually surprised that there's as many of you that came to class. So great, good. We're gonna have a good class. In case I forget to say it later, happy Thanksgiving. I hope you guys have a nice holiday, whatever you decide to do for the holidays. Yep, that's 31 of you. That's actually a lot more than I thought. All right, so again, there were no discussion sections this week, and then there's no classes, no office hours, no anything on Thursday and Friday. And there's no quiz, but next week, don't forget to go back to your discussion section. It'll be the last week. It'll be your last quiz, your last chance to increase your score or to keep it good and to ask your questions from your TAs. The final exam will be in person. I'm trying to work the details about how to do a review, but I will let you know after the holiday. And also, if you remember to fill out the evaluation for this class, it's always very helpful to get your feedback. So today we're going to talk about galaxy collisions. And, in case you have to leave early or whatever, let me try to give you the entire class in a nutshell. Let's see, let me try to do it in 1 minute. So galaxies tend to live in groups. Sometimes they're big groups, sometimes they're small groups, but they usually are in groups where the relative distances to each other are kind of small. So for this reason, because they're moving around, they sometimes run into each other and they collide. When that happens, they completely lose whatever shape they have. So that may seem like a bad thing, but in reality, nothing like actually really bad happens. And in fact, some good things happen, and I'll get to that in the class. And our galaxy, the Milky Way, has been in a couple of collisions already, and I'll tell you about them. And also in the future, there's going to be a major collision between us and our neighbor galaxy, Andromeda. And it's way in the future, as the video that I was just playing talked about, but it'll be actually quite beautiful. So that's the entire class in a nutshell. It's of the violent things that we talk about, this is the one that is kind of the most beautiful and that doesn't lead to destruction, doesn't lead to death. On the opposite, on the contrary, sorry, it actually leads to life. But, and I don't mean human life, I just mean like new things appearing. All right, so that's the class in a nutshell. You can fall asleep now. No, just kidding. All right, so we were talking about galaxies. We talked about how the Milky Way is a spiral galaxy, and there are 3 major types of galaxies in the universe. There's spiral galaxies, and those spirals subdivide into regular spirals and then barred spirals, the ones that have like a line. There's elliptical galaxies, and then there's irregular galaxies. The most common type is the spiral galaxies, followed by ellipticals, and only a very small fraction of them are irregular. So, as I said at the beginning, galaxies like to live in clusters. I mean, it's not that they like it, it's just that they have a lot of gravity, and their gravity tends to attract more things. And so you find whenever you see galaxies, for the most part, you find them in clusters. Now, some clusters are rich, some are poor. They are classified into richness of cluster depending on how many stars they have. So you call it a rich cluster if the cluster of galaxies contains hundreds or even thousands of galaxies. They tend to be, well, I'll tell you more in a second. So a rich cluster if it has a lot of galaxies, if it has hundreds or even thousands of galaxies. A poor cluster of galaxies is also called a group, a galaxy group. And that only contains, between a handful and maybe a few dozen, but it doesn't get to hundreds of galaxies. So rich and poor, and the poor one is also called a galaxy group. Our galaxy, the Milky Way, belongs to a group, and it is not a rich group, it is a poor cluster. So our galaxy is a member of a poor cluster that has a very imaginative name. It's called the local group, right? I mean, we couldn't come up with something better. But it is just a few galaxies. In fact, the Milky Way, which is pictured here, a cartoon, obviously, is, you know, a large galaxy, 100,000 light years across. And then there is another galaxy in the group, which is called the Andromeda Galaxy. We've alluded to it a few times. The Andromeda Galaxy is about the same size as the Milky Way. It's about twice as big, right? But it is still in the same order of magnitude as the Milky Way. So those are the two big galaxies in our group. There's also a triangulum galaxy, which is a smaller, much smaller spiral galaxy. And other than those three, everything else is what is called a dwarf galaxy. So these are galaxies that are much smaller than the size of the Milky Way. And some of them are irregular galaxies, like these two here. Those are the Magellanic Clouds. You can see them from the southern hemisphere with your naked eye. Those are irregular. Some of them are elliptical. Some of them are like tiny little spirals. Andromeda is a spiral galaxy. So you see it a little bit in profile, right? We were talking about spiral galaxies having disks. And so you're seeing it not quite edge on, you're seeing it sort of, you know, at some degree, some number of degrees. So here is the bulge, and this is the disk of the Andromeda Galaxy. And then you can't quite see the spiral arms because they're sort of obscured by the dust, but it has spiral arms. So it is a spiral galaxy. All right, so this is just to show you more or less the location of things. So if the Milky Way, I mean, from our point of view, we're the center, but the Milky Way is here, Andromeda Galaxy is over here, and then there's the Triangulum Galaxy over here, and then all of the other ones are little dwarf galaxies. And of course, you don't need to remember any of these names other than Andromeda, because you should know that our biggest neighbor is Andromeda. But there's many other tiny galaxies, and they find more and more pretty much every year. But they're all tiny, right? That's the point. There's no big galaxies other than Andromeda and Triangulum around us. So this is called, again, the local group. Here's another example of a poor cluster or galaxy group. This, for example, is called the Hickson Compact Group. And you can see how, just like in the case of our local group, you have every type of galaxy. You have some spiral galaxies, some big ones. This one, it looks weird. It's probably a spiral galaxy that is, again, edge on. So that's why it looks like that, but it probably has like a bar or something. So it's the kind of galaxy I would never give to you in an exam, right? Because it's really hard to figure out what it is. But it has a little spiral, a very large spiral. It has an elliptical galaxy over there and a lot of little dwarfs. So that's usually what groups of galaxies or poor clusters look like. They have all types of galaxies, almost always spiral galaxies. In contrast to that, when you look at a rich cluster of galaxies, like this one here, every yellow thing that you see here, yellow, reddish, that's a galaxy. And you can see how the vast majority of them are elliptical galaxies. And then you see some that look like, oh, this might be a spiral, or maybe it's more like a lenticular. You know, lenticulars were the ones that were in between spirals and elliptical. But the vast majority of them are elliptical galaxies. So I want you to remember that. Remember that rich clusters have hundreds to thousands of galaxies. So they're very, very large. And almost every galaxy in rich clusters are elliptical galaxies. That's an interesting thing. It's an interesting difference between poor clusters. And later in the class, we'll see probably the reason why this is the case. The other thing that is interesting about rich clusters is that very often when you look at the central part of the cluster, you will find something that is called a giant elliptical galaxy in the center. This is a galaxy that is just 10, 100 times, sometimes even 1,000 times bigger than the average galaxy. So here's an example in some cluster called the Abell S0747 cluster. Here's a giant elliptical galaxy. And you can see, so this would be another galaxy right in the cluster and another galaxy. And you can see how much bigger they are. And again, I want you to keep that information in mind because later on we'll see why this may be the case. Why is it that when you have a very large cluster of galaxies, most of the galaxies appear to be elliptical, and then you have a giant elliptical in the center? So keep those things in mind. So with that, let's turn to galaxy collisions. And this is actually a picture of a galaxy in the process, or two galaxies in the process of colliding with each other. And it's a picture, it's not a cartoon. All right, so as I said before, galaxies tend to live in groups or in clusters. And so they're relatively close to each other. And they stay together because of their mutual gravity. And later on next week, we'll talk about how the universe is expanding. And even though the universe is expanding, galaxies in groups, they feel the gravity from each other pretty strongly. So then they tend to stay together. Now they move in orbits, right? Everything in the universe pretty much is moving, and everything is sort of orbiting something else. And in the case of a cluster, they're orbiting the center of mass of the cluster. And as they move, sometimes they run into each other because they're pretty close to each other relative to their sizes, right? I mean, if you take it in absolute terms, I mean, no, the distances between one galaxy and another are huge. But compared to their sizes, they are pretty close. I mean, let me go back to this picture. I mean, you see that galaxy relative to its size, this galaxy is not that far away, right? I mean, if this was a person with their arms stretched out, they're at 1, 2, 3 arm lengths away from the next person or the next galaxy. So they're, compared to their sizes, they're pretty close to each other. So here's one thing. We've known for a while that galaxies do this, that they run into each other. We see pictures of galaxies sort of caught in the act as they're colliding with each other. But the problem is that the process takes millions of years, right? Because like I said, in absolute terms, these are gigantic distances that they have to go across, and even their sizes are so big. Even if they're moving fast, they're still going to take a while to run into each other. So because it takes millions of years and we don't have the benefit of being able to just sit down and wait until they collide, we have to use computer simulations. So this is a field of astronomy where we really rely on computers. And the way that that you do this is you code all of the physics that we know into a program, right? Where you get a simulation of a galaxy and a simulation of another galaxy. And then you have to include everything, gravity and dark matter and gas pressure as stars form. And as the temperature rises, the gas pressure has to go up and just stuff like that. And then they make them run. And this is how we can learn about what happens and in what order when galaxies collide. So I have a couple of videos about numerical simulation. So just a little introduction. Let me play those.
This is a galaxy. Okay, so it's not a real galaxy. For one thing, we can't do this with real galaxies. No, galaxies are too big to fly through. This is a digital galaxy. A digital galaxy really looks like this. Vast numbers of numbers detail the distribution of mass in the Big Bang of the virtual universe. A computer uses the laws of physics to evolve the universe through time. Here is the dark matter, which is best known for being dark. But in the virtual world, anything can be illuminated. Dark matter can be green, if you like green, which I do. The visible universe looks more like this. Well, actually, that's a bit of a cheat too. We're taking virtual pictures of the gas, the stars, and the gas that's turning into new stars, giving them any colour we like, then combining the layers. But it's not too much of a cheat. Pictures of real galaxies are often coloured in this way too. Wait a few billion years in the real universe, or a few hundred years for a computer, or a few months if you've got a supercomputer, and then you have a galaxy. Well, you could have just looked at the sky, but we still make virtual galaxies because they help us study where the real ones came from.
All right. All right, so there's a question about if there's a middle of the universe, if there's a center of the universe. We'll talk about that next week, but the answer is no. The universe, we think, is infinite, and if something is infinite, you can't have a center. In order to have a center, you have to have edges, right? You have to have and the universe doesn't have edges. So even if it's not infinite, it sort of curves onto itself, and so it doesn't have an edge, and for that reason you can't have a center. And we'll be talking a lot more about that. Do we know about the origin of the universe? We'll talk a little bit about the Big Bang, which is currently the best theory that describes how the universe began. And right, so okay. So anyway, so that describes how we tend to study the universe. In the video, it was talking about how the universe changes over time. And in particular, like in this video that I'm going to play now, I mean, this is just showing you how simulating how galaxies collide can look a lot like the real universe. So this simulation goes, it starts with two spiral galaxies, and then it kind of switches and shows you real pictures of galaxies. So this is what the simulations tell us, that as two galaxies get close to each other, their shapes begin to change. And by now you should be familiar with why that happens. This is because of tidal forces, right? Tidal forces meaning gravity pulling harder on one side than on the other. And you can see how these two disk galaxies or spiral galaxies, they started off as being very nice and symmetrical, but as they run into each other, gravity pulls harder at one side than another side, and they form these things that are called tidal tails, right? So tails that are launched because or pulled apart because of gravity. And again, you can see how the simulations describe very much what we see in real life with telescopes. And here continues the simulation, and you can see how certain things happen, well, that I'll get to in a second. All right, so let me just say, question about are there theories about the end of the universe? Yes, and we will get to them next week. Right, so during a collision of galaxies, like I said, the shape of the galaxy changes, and it changes because of gravity. However, as you've seen maybe you've seen in videos about collisions of galaxies, stars do not collide. And actually, since there are only 42 of you, let me open the chat. I think it might be manageable. So, all right, everyone can write to everyone. Tell me why you think that stars do not collide during a collision of galaxies, right? So a galaxy is made up of stars and dark matter and interstellar material. And when they collide with each other, stars actually don't collide with each other. Yes, so because it's mostly empty space, right? Even though they're huge and it's not dense enough, that's another way to say it. The density of stars is not huge. There's actually a lot of free space in between stars. And so they can go through each other. So remember the analogy that I gave you, or the comparison that I gave you. If the sun were the size of a tennis ball, the nearest star would be in Seattle. So just think about all that empty space. And now imagine a galaxy made up of a whole bunch of stars, but with huge empty spaces in between any two stars. So when galaxies collide with each other, they, even though, again, the shape of the galaxy changes, the stars themselves, for the most part, go through each other, right? They're able to pass by each other. Can they ever collide? Can two stars ever collide? Yes, of course. But the probabilities are tiny, like one in 100 billion, for example. Something like that, right? I don't know the exact, it depends on the galaxy collision, but the probability is tiny. So in other words, if you have two galaxies of the size of the Milky Way colliding with each other, the probability is that only one, or your expectation is that only one star will collide. And so in our case, when we collide against Andromeda, we're probably not going to be the one, right, that collides with another star. So, right, but it's not because everything is expanding. We'll talk more about the expansion of the universe. Don't think about the expansion of the universe yet. All right, whereas stars don't collide with each other when there's a collision of galaxies, interstellar material, gas and dust, does collide. Clouds of interstellar material do collide. And why? So why do you think that stars don't collide, but clouds of interstellar material do collide? Any ideas? Like in the video? Oh, because it's too hot. No, maybe I'm not asking this correctly, but imagine, I mean, if these are the stars, it's more massive. Sort of, yes. Well, more dense, right? So interstellar, the word implies they are in between stars. So clouds of gas and dust fill the space, or can fill the space in between stars. They're much bigger. Clouds of interstellar material are much bigger than stars themselves. Remember that a cluster of stars comes from a huge cloud of gas that can actually give birth to hundreds, thousands of stars. So that means that the probability of those clouds colliding with each other is much higher. And what happens is, when those clouds of interstellar material collide with each other, then star formation can be triggered. right? So a lot of the times when you have a collision of two galaxies, if they have plenty of gas and the gas collides with each other, right? Clouds of gas collide with each other, then a lot of the times that's going to give birth to new stars. Why? It's not necessarily obvious, right? Because there are various competing things, and some of you have talked about heat, right? So if you have a collision that results into increasing the temperature, then of course you're not going to have stars. But a lot of the times, you know, the collision is slow enough that the gas are just compressing, the gas clouds are just compressing each other. When you compress gas, that means, yes, the temperature is raised, but if you can compress it slow enough so that it cools off, right, then the density will increase. And just like in the Milky Way, well, I was telling you that the density waves from the spiral arms can cause gas to be compressed and then to get star formation. The same thing can happen when two galaxies collide with each other. So this is an actual picture. This galaxy is called the antenna. And you can see what happens when the two centers of the galaxy are colliding with each other. Here are the tails. And when you take a Hubble Space Telescope picture of the very center, you can see how there's a lot of blue regions, and those are baby stars that are being formed. And there's an enormous amount of star formation that is happening here in this antenna galaxy. And we see it pretty much everywhere. Whenever we see collisions of spiral galaxies that had a lot of gas to begin with, and they collide with each other, you get much, much more star formation that would be normal for a spiral galaxy. So we call those starbursts, or bursts of star formation. And so again, it's the stars don't collide, but the clouds of interstellar material can collide, and that can give birth to a lot of stars. So an increased amount of star formation. And last time, several of you were asking me about, not last time, but over the last few classes, some people were asking me like, so how do you get star formation? You know, we talked about stars form when a cloud of gas, when the conditions in a cloud of gas are the right ones, high density, low temperature. But how do you go from a cloud of gas that is not forming stars to one that is forming stars? So now I've given you two answers. One of them, spiral arms, the density waves. That's one way to trigger star formation. Here's another one. When you have a collision of two galaxies that have a lot of gas, then you can trigger a lot of star formation, a lot more than with just density waves. Right, so I have a question about this video. In this video, you see some stuff sort of flying off. It's a little, I should probably explain a little more what you're seeing in this video. You're seeing more so the gas than the stars. Can some stars be flown off? Can they be ejected from the galaxies? Yes, absolutely. Just like, I mean, we've talked about cases where, like in the case of comets, you know, like sometimes the gravitational interactions of one with the other sends one of the comets into the solar system. But the opposite can happen, right? Gravitational interaction can send a comet off the solar system. And in the same way, when you have two galaxies colliding with each other, it can send some of the stars away. But what you're seeing here is not stars. You're actually seeing gas. And it probably would take me the rest of the class to explain in detail what's happening. But part of it is, you see some of that gas disappear at some points. And what's happening is the gas is becoming stars. And that's why you don't see it anymore as gas. But the other thing that happens is some of those baby stars are very massive and they explode as supernovae very quickly, right? Because you're watching here a couple billion years, worth of time. So in that time, you can get those stars exploding as supernovae. And those explosions that you see, those explosions that happen is what you see why it looks like things are being flown off the galaxies. It's also possible that each of these galaxies has a supermassive black hole in the center. And as they merge, these two supermassive black holes merge together. And then there is an accretion disk around them. They become, AGN, which we talked about before. And that accretion disk can also blow a lot of the material out from the galaxy. So this is actually exactly what I study currently what I study in my research, how supermassive black holes with accretion disks around them can actually blow away a lot of the gas from from a galaxy, sorry. So thank you for asking that. All right, so here's another example where you see galaxies colliding with each other. And you can see some of the parts of the galaxy look super blue. And, here is a tail of stars and gas that is pulled out from the interacting galaxies. But obviously there's quite a few blue stars here because you see blue light. Here you see a bunch of stars sort of on the head of the galaxy. And then you see some material flowing in between the two galaxies. So as I was saying at the beginning, this is the one violent thing that we talk about where, you don't necessarily die if you're in a galaxy and the galaxy collides with another one, but you might see some really beautiful displays of new baby stars, lots of light, right? It's a little bit like fireworks, because if a lot of stars are created, then it's going to look very beautiful. Now, let me get back to some of the characteristics that I told you about elliptical galaxies versus spiral galaxies. And let's see if we can explain some of those differences because of collisions. So it turns out simulations of collisions of galaxies can show that two spiral galaxies can merge to form one elliptical galaxy. And you saw it in this little simulation here, right? So you start off with two spiral galaxies, they run into each other, they create these tidal tails. And notice how first they pass by each other because they're going pretty fast. So they want to keep going in their orbits, but then they slow down because of the gravity from each other, right? So they go by and they slow down and they come back to each other. And then they start going on this dance, going back and forth until their gravity just pulls them in and they become one. So these are merged galaxies. If you give them enough time, all the stars are going to be, instead of being those nice orbits where all the stars are going in the same direction, right, in the disk galaxies, if you give them enough time, they're going to be messed up enough that they're going to be going in different random directions. So when that happens, a galaxy is no longer a disk galaxy, it's no longer a spiral galaxy, but it becomes a bulge that has stars with random orientations, and that's what we call an elliptical galaxy. So two spiral galaxies can merge and form an elliptical galaxy. What do galaxies orbit? Galaxies orbit the gravitational center of their clusters, right? Where the mass center is in a cluster. So Let's see. All right, so if you remember, I had a slide like this last time, telling you about some of the differences between ellipticals and spirals. So now we know that collisions can explain some of the differences between spirals and ellipticals. So I told you last time, ellipticals can be more massive and more luminous than spirals. Why? Well, because ellipticals can form when two or more spirals merge. So obviously the product is going to be more massive. So if you have a bunch of spirals that collide and form a new elliptical galaxy, then it's going to be more massive. And that's why that you can find ellipticals that are way more massive than spirals. That doesn't explain why you can have smaller ellipticals, right? So it doesn't explain everything, but it does explain some things. I told you last time that ellipticals have very little gas in contrast to spirals or disk galaxies, which have a lot of gas. So how would collisions explain this? Well, when you have the collision between two spiral galaxies, when they collide with each other, there's a lot of star formation. So like in the video, right, where the gas disappears. And that's because the gas turns into stars. And then instead of having a bunch of gas, you have a bunch of stars. And those stars evolve, they get older. And then over time, they become this yellow. I mean, all you have left is the yellow and red stars. And so that's why you end up with galaxies that have very little gas, because most of the gas was used up in forming stars during the collision. And finally, there are fewer ellipticals than spirals. Well, that's because they're just forming, right? So if you start off with mostly spirals, then as they collide, you start to build up an elliptical population. And then it'll take a while, right, for more and more spirals to merge in order to form more and more ellipticals. So I'm qualifying it here because the formation of at least the larger ellipticals, right? We're not talking about the little ones, but at least the larger ones, that requires a merger of spirals, and that takes time. So right now, there's more spirals than ellipticals, but give it enough time in the universe, and eventually we will have more ellipticals than spirals. I give it a lot of time, right? It'll take a long time for that to happen. So I don't want to give you the idea that all of this is 100% proven or anything like that. These are ideas that we believe that are the best explanations so far about elliptical galaxies. But of course, there's a lot of research that is going into this and trying to explain what we observe with telescopes. All right. Collisions may also explain why elliptical galaxies tend to be found in rich clusters of galaxies. So I told you rich clusters of galaxies have mostly ellipticals. Why? Well, because you have a lot of galaxies, they're very close to each other, so the chances are that they ran into each other. This also tells you that these large clusters of galaxies are very old, right? Because they need to have had enough time throughout the history of the universe for all those spirals to run into each other and form elliptical galaxies. But it may very well explain why rich clusters of galaxies have mostly elliptical galaxies. One more thing that collisions of galaxies can explain. So I told you that often there is a giant elliptical galaxy in the center of a rich cluster. Well, what may have happened is what is called galactic cannibalism, which is when galaxies, they're in close proximity to each other. And even if you start off with spiral galaxies, they run into each other and then they get into this dance because of their gravity. So their gravity attracts them. And even though this is going a little too slow, but let me speed it up, they start to go on this dance going back and forth, and then they merge 2, they merge 3, 4, 5, and in the end, all of them merge together. And then you end up with a super galaxy, right? You end up with possibly a giant elliptical galaxy. Here in the top, you see actual pictures of different groups of galaxies, and you can see them at different stages as the galaxies get closer together. And are forming a bigger and bigger galaxy. In the bottom, you see just snapshots from the simulation. So giant elliptical galaxies are probably the result of galactic cannibalism. So here are some pictures of different interacting galaxies. Have them in my background too, as observed with the Hubble Space Telescope. I just love how beautiful they are. And again, it's violent, but it's beautiful. And this is actually something that really inspired me when I was a grad student. And it caused me to do my research in colliding galaxies, because they just look so awesome. And so my research was actually what's the relation between galaxies colliding and the black holes that are in the middle of the galaxies, what happens with them. So anyways, there's some types of galaxies capable of catalyzing and maintaining more life. Oh, that's a very good question. I can say the opposite, right? There are some types of galaxies where life would be more difficult, just because if you have a supermassive black hole in the center that is accreting matter, that is an AGN, then you get a lot of radiation coming out from the accretion disk, right? That's why they're super bright, the AGN. So it might be harder to have life at least close to that accretion disk. Whereas our galaxy, our black hole in the center of our galaxy is not doing much. It's not eating, right? I mean, sometimes a little bit of gas goes in, but there's not an accretion disk around it. And so life in our galaxy is a little bit easier. Do irregular galaxies have supermassive black holes too? So irregular galaxies like all of these would have been classified in the early days as irregular galaxies because they're asymmetric. They don't have a very clear bulge or a disk. So in these cases, they do have supermassive black holes. We know that, right? I mean, they're just galaxies that are colliding, and they have 1, 2, maybe 3 supermassive black holes. But there are other irregular galaxies like the Magellanic Clouds, like the little ones that are near our Milky Way. Those we don't know. We don't know if they have supermassive black holes. And that's actually part of my research too, what I'm doing. We're trying to figure out, do they have, and they wouldn't be supermassive black holes, they would be what are called intermediate mass black holes, but we don't know yet. So good questions. All right, so if you look at a galaxy, this is kind of a fun thing, in research, you can play archaeologist with galaxies because you can see a galaxy as it looks today, and you can try to reconstruct what happened to it based on, certain telltale signs of, that they have gone through a collision. So some of the things, I mean, you don't have to memorize this, but just some of the things that you can find. You don't have to, well, maybe you do have to memorize, I don't know. But just the idea, right? That if you see a galaxy with tidal tails, you know, where gravity pulled out some of the material, or a bridge where again gravity is making go some material go between two galaxies, then that's how you can know that the galaxy either is undergoing a collision or it did in the past. And there are others like rings, a disk that is warped, a disk where gas is going in one direction and stars are going in a different direction. Polar rings, that just means, you know, going where you have a ring going through the pole, or shells, which are sort of the leftover from the collision. So all of these things can tell you that a galaxy went through a collision or is currently going through a collision. So what about the Milky Way in the last 3 minutes that we have? Has the Milky Way gone through an interaction? And the answer is yes. We do detect some of this signs of interaction that I showed in the last slide. And at least at the moment, as we speak, there are currently 2 ongoing mergers. These are what are called minor mergers. A minor merger is when you have a big galaxy with a small galaxy. So the big galaxy kind of doesn't feel much of it. The small galaxy, on the other hand, the dwarf galaxy, gets completely torn apart because of the gravity of the Milky Way. And so I had this simulation where, you know, you don't see the Milky Way. You only see, it's supposed to be going around the Milky Way, and you see the dwarf galaxy, and the tidal forces just rip it apart. And so, you know, here's the Milky Way in blue, but in red, you see sort of the streamers of the stars from the dwarf galaxy. And there's at least 2 of them that we can identify. One is Canis Major, which is the simulation that I showed. The other one is Sagittarius A, which is, interestingly enough, do I have time to tell you? Yes, I do have time. So this is an article that just came out last year, where they figured out when they follow, you know, they've been able to measure the orbits of all of these stars from Sagittarius A dwarf and from Canis Major dwarf. And they can figure out, they can trace it back, like how long ago did this merger start? And it turns out for the one with Sagittarius A, with the Sagittarius dwarf galaxy, turns out that that little dwarf was going through the location of our current sun about 5 billion years ago. And they figured out, again, this is like archaeology, that about 5 billion years ago, this satellite triggered star formation right around where the sun is. So chances are our sun came as a result of this interaction. So as the little dwarf was going around the Milky Way, it triggered a bunch of star formation, and then possibly, right, we don't know for sure, but possibly our sun was born because of this interaction. So again, this is the part where we do violent universe, but that actually possibly led to the formation of our sun. Last thing, oh, it's already, well, I mean, you've heard about this a million times already. Our Milky Way is in a collision course with Andromeda, our nearest neighbor. That's going to take several billion years. When it does happen, it'll look really cool. You know, Andromeda is going to start looking bigger and bigger and bigger in our sky. Then there's going to be all this beautiful star formation, and you'll see the distorted galaxies. And eventually, after many billion years, you will see a giant elliptical galaxy in our sky. So that's where I'm going to leave it. Have a wonderful Thanksgiving. And I will stay here for a few minutes to answer questions. And I will see you on Monday otherwise. So let me stop recording.